Okay, hello everyone. Welcome back to the Kai lecture. Today is our 12th session. It's on explanations. So last week we had metrics. The second session of this year is going to be about explanations, causal explanations, of course, in the context of AI, XAI. Today, I'm competing a little bit with another lecture, which is a special occasion, actually. So from 2 to 3, there's Moritz Grosse-Wenzel. He's a professor in Vienna, and he's doing amazing work, also on causality and also on at least parts of the things we are going to see today, actually. So he's here today in Darmstadt. I mean, I don't mind you if you're running out of this here, but I think it's going to be recorded, so you can also catch up to that one. But then again, this one is too, right? So feel free. But if you're staying with me, I'm super happy because, Moritz, he already went, and so some others as well. But yeah, so that's what we're going to do today. But what is the overview? So we are well into the year now, and also no holidays, anything. So no overview decorations anymore. It's just straight to the point. Today we are going to do the same style as last week. So last week, essentially, we just went over 3 recent works in the scope of metrics. And today we're going to do the same in the scope of, well, explanations. And as you can see, we have also one of our works here, the AI/ML Lab, an ongoing project, right? It's been going for a while. It's rather that it's unpublished yet, but that's a different story of its own. It can be difficult at times. But the other 2 ones are published. So this one was NeurIPS back then, and this one was at the very first edition of the Causal Learning and Reasoning Conference. C-explain, counterfactual explanations, and structural causal explanations. So these are the things we're going to look at. But as last week, right? Last week we did like a first disclaimer of how are we going to treat this? What are metric spaces and things like that? And so we're going to do the same now here for explanations. And let's start with feature importance, because probably a lot of you are aware of these things, given that this is also a master's course and people are anyhow interested in machine learning. So feature importance is kind of has been a standard for a long time. It's been an established way of going about doing explanations, right? So what you can see here on the slides is, what I deem also very successful works, because it really has been everywhere and blog posts on Medium or wherever, right? Being just, written to talk about these ideas. One of them was, GradCam, published in 2019. Actually, the work is older, but it only got published in 2019, so I know that feeling. And it really just goes into the original space of the features, the input space, which in this case are the images, right? And it highlights decisive features, decisive in the sense of they were key components in doing the actual prediction, right? So let's say we had a classifier, right? And say the neural net is focusing on one of the 2, or say on the foreground, then the neural net would say this is a cat, right? And what this GradCam method can do now is produce essentially a heat map, a mask overlay, befitting of the original image, highlighting the area that contains these decisive features, right? In this case, the pixels, which were most important for, according to GradCam, for the neural net to choose the prediction cat, right? And as you can see, it's actually highlighting the cat. This is what we want to see, right? Also, what we can see is that maybe the butt of the cat here, right? So the behind is being focused more upon. Well, one interpretation that I could give you is, the stripes, I guess, right? Stripes you don't typically see in that kind of pattern on dogs, right? So kind of makes sense. But as my dear colleague Wolfgang Strammer would say, this is not really an explanation in a lot of ways, right? He makes this nice metaphor of, it's like a child, pointing to something, but not being able to say anything about it, right? Like asking, oh, what is it? And, it's like, yeah, look at this, right? And then we fill up all the blanks, right? But still, it's an amazing achievement, right? And it has worked in many ways, really revealing a lot of things, right? At the end of the day, what we're trying to do is really debugging, right? Like we are trying to understand the decisions of the model, right? And that's a good thing. And we got to start somewhere. But yeah, with that, let's move on to where it fails, right? The fallacies. And I guess, to me at least, the most iconic fallacy of all is really the clever Hans situation. So what you can see here on the right-hand side of the slide is we have these two rows, well, both the same image, and then the breadcam style visualization, the attribution, yeah. But what you can see is that in the image where we have this tag, right, where it's somehow related to, I guess, the photographer, right, and then there's a website. Yeah, I think it's something like Pferdefotoarchiv, so horsephotoarchive.de. And well, the model is predicting correctly that there's a horse on the image, right? But then you look at the attribution and it sees like, oh, it's just looking, oh, there's this thing, right? And does not even have to read that it's horses, right? But there's just this thing. It's always some pictures with horses, so got to go with that, right? It's easier for me to predict. One of the reasons as well, right? I mean, optimization is the huge deal of deep learning, right? And this just makes optimization a ton easier. If we now remove this tag, suddenly we don't see the horse anymore, right? Which to us as humans is very weird. It's very reminiscent of an adversarial attack where, there's a panda image and you see it as a panda and there is suddenly a noise and now your neural net thinks it's a gun, although it's still a panda, right? And that's really what's happening here, right? And back then in Nature Communications 2019, Lapushkin et al., they really gave an assessment of, they were just using this figure, but then, doing a thorough analysis on when these predictors really fail, right? And well, I guess this is also, part of the reason why we are trying to do this, right? Because we know that these neural nets can do these kind of weird things, right? These shenanigans. Where does the clever Hans thing come though? So as you can see, it's also put in quotations, and we as Germans, we might say, oh, Hans, that's a name, we know that, but like it's actually an established term in the community. Where does it come from? Well, it comes actually from a horse, which was called Kluger Hans, Clever Hans, right? This was the date, so end of 19th century, transitioning to 20th, and it seems so. I guess this is an original photo. I just took it from Wikipedia, yeah. But what you can see is this whole crowd standing just around Hans, right? And it was believed that Hans was able to perform arithmetic, right? So simple things like 5 + 3, and then they would, I don't know, knock 8 times, and then Hans would do some kind of reaction for them to trigger to say, oh, he's meaning 8 is the solution, right? And he would do it every time, right? It was fascinating. Later on, there's, it's a bit controversial, but I think generally the consensus is that really Hans was amazing at picking up body language. So every time, we were approaching the right answer, the human would get nervous. Oh my God, he's so close, right? And Hans would feel that and then say, stop, it would just work, So at least that's how I picked up this real world story of Hans. Right? Good. Returning to XAI, or maybe just stating what XAI is. As you can see, XAI is just explainable AI, and the X is being just put on because it's cool, it's put in caps. And what we can see here is from Bean Kim, a plot from DLSS 2018. So obviously the plot is being cut off we see 2017 here, but it's really showing across the x-axis here on the horizontal that over the years, the number of papers which are involved somehow with interpretable machine learning, right? And bear in mind, I'm not trying to define what interpretation is, explanation, whatever, right? Like we are going to do that in a very different way, in a lot more pragmatic way, right? And it's not about the details of where these numbers necessarily come from. We just see for certain that there is a trend going on, that people are trying to understand these models, and it makes sense. You can see that this actually started, this is maybe the more interesting thing. It's not with deep learning and the rise of these models, say ImageNet moment and then 2010s and onwards. No, it's actually already in the 90s and end of 90s, right? Actually, if you look kind of on this particular plot, it seems like it's actually had slowed down a little bit. Maybe people stopped caring about, as soon as deep learning hit the shelves, because they were like, oh, this is so amazing, right? Like everything works. But no, I think certainly, like especially the last few years, especially in the realm of causality becoming more and more mainstream, right? Me being here holding this lecture to you, right? I think it has, again, gained some traction. Maybe there's a plateau, and I would postulate that it's going up a little bit again. But yeah, that's what we are seeing. And the reason is, well, clever Hans and all these kinds of things, right? That we are trying to solve these things. So we have powerful models, and they get put into more increasingly important roles, right? And they have somehow higher responsibility, right? So we want to understand, we want to trust at least, right? And so that's, I guess, one of the key factors. So as last week, just a quick disclaimer on how we're going to treat this. So in this case, causal explanations. Again, causality, as you have seen, that this whole lecture so far, right? It's really like, yeah, I mean, there's different ways of going on about it, right? And some might make more sense than others, right? But really, it's about defining this, right? And trying to capture the ideas. Same goes for explanations, right? And so these things are really up for debate. That's why I put it in bold here. And, you know, philosophers discuss this, cognitive scientists, mathematicians, we discuss this, everyone does, right? And so what we're going to do is simply focus on the works that have been put out in this area, right? And how they consider these terms, because they do take a clear stand, right? Even if they don't write explicitly, explanation equals this. Clearly, when they talk about explanations in their paper, they're taking some kind of position, right? So they are assigning what it should mean, right? Both separately, but also in combination. And again, these might not be to your liking, right? And that's actually a good thing, because we need fresh and new ideas and to challenge existing ideas to, well, improve overall, right? Yeah, so some of them might not even be that rigorous, right? They might just be some hand-wavy intuition on what any of these terms should mean. But yeah, there's you know, it's a spectrum, right? They all fall somewhere in that. Okay. Anyone want to talk about XAI? Any particular funny story they might have with XAI? Anything they've seen in that context, or any thoughts? How many of you have worked with XAI and stuff like that? Maybe just to get an impression. Okay, well, I guess with the seminar or Causality, was it, or before that? Okay, but yeah, you wanted to say something just like.
Did they reach?
Oh, I don't know. I would have to check up on that detail, right? So you're saying whether, you know, it always whether the model could still pick it up essentially, right? Yes, the model can, of course, pick it up, right? But it's a bit more difficult to optimize, right? Because, you know, there's a lot of variation factors in an image, right? It could be a horse in winter. It could be like in the picture in spring, right? All these different variations, but the tag is always probably the same in white, maybe. And right, so it's a lot easier to pick up, right? But still, obviously, it works, right? And that's what they do, right? They augment the data, they manipulate somehow, right? To you know, de-bias the data or something, right? So definitely it works, but it's a bit more difficult, of course. Yes.
But a similar story to yours, where a model was trained to recognize fish in fishing pictures. So you had a guy with a fish holding it, and the model was supposed to recognize what kind of fish it is. And for some specific kind, I think some kind of cod or something, they did the same analysis and find that the model was specifically looking if the finger of the guy was like under the fish, because that's one like very specific detail that identified this kind for some reason.
Yes, and that's exactly these kind of things. Actually, I'm thinking of a very similar example, which was for COVID, where they had like these X-ray scans. And as you can imagine, this like a high stakes medical setting, not just because it's personal, but especially because it's, you know, having implications on what kind of treatment they might get and so on and so forth. And there was these images where there's, I don't know, some kind of, I'll just call it artifact of the same kind, right? I think when they took the X-ray, they put something there for everyone who had COVID, right? And then the model just picked up that, right? Because the model is smart and, you know, picking up the statistical properties of the data, right? Like that's what it's supposed to do, yeah? But then, you know, we fail to recognize this, and then that's when everything goes horribly wrong, right? There's also the very famous, maybe you've heard about it, the urban tank legend in machine learning. There was this model which can classify tanks, Russian and American ones, right? And it was like perfect, right? But then they realized, oh, the Russians one were always in winter, right? And so like, yeah, screw that system, yeah. So exactly, it's these kind of things. Yeah. So there's different techniques, right? So with GradCam, I would have to look up again. I think they're just using somehow the gradients, right, of the right, just like you do back propagation to, you know, get the effect that your weights have, changing the weights on the error term, right? Be it, you know, cross entropy for your classification, or MSE for your regression or whatever. And I think they can do a similar type of thing there. And then there's distinction. There's this, for example, this layer-wise back propagation. I think they're even more specific on that one. and then all kinds of variations from taking integrals and so on and so forth. But generally, you're trying to figure out, right? Like there's ways of, for example, masking, right? Like you take out these certain pixels and now see what the prediction would be. How drastic is it changing, and so on and so forth. I'd say in my experience, all of these methods work quite well. But then again, a lot of these operations are parallelizable and so on and so forth, right? So we got to think a little bit like, large scale computers at times as well, right? That they can, because it's repetitive tasks, right? So, and there's obviously a lot of tweaks as well and stuff like that. But then again, yeah, there's also techniques which are more expensive. And naturally, if you go for any kind of exhaustive thing, that's going to take more time. Okay, cool. If there's nothing else, then one more disclaimer, just like last time. Generally, notation we are going to take from the works, right? I might adapt it here a little bit, but in general, to make you accustomed, to be more faithful to original thing when you go back and so on. But yeah, now let's jump into our first reference. So Patrick Schwab and Walter Karlen from ETH, they in NeurIPS 2019 got out their method C-explain, causal explanations for model interpretation under uncertainty. Big name, big paper. I think it's been one of the more popular ones. Works well. And we're going to dive in here now. So there has been, as I've been already alluding to right now, a lot of, competitors over the time, right? This is like a very popular field, I mean, images, again, computer vision as a whole field. I mean, conferences like CVPR, right? They just run and they are just big, and it's a huge interest, right? And obviously that then goes also for XAI, especially when XAI is so image focused, right? And so as you can see, there's plenty of references here, right? So as you can see, three of the five here are from 2017. One was from the year before. The earliest was from 2014. By no means is this exhaustive. This is actually what the authors looked at here. And then they simply compared this to C-explain on 4 dimensions, obviously favoring them, but for good reason, since, their model is model agnostic. So really doesn't really matter if it's from a neural net or anything, right? So it's a kind of post hoc explanation scheme. So that works well. They get uncertainty estimates, which is also in the title, which is important, right? So they're trying to capture somehow or quantify, well, when is our model good and when not. And these models are actually very fast. I can say from experience as well. And well, accuracy high, I guess, in some kind of relative notion. As you can see, most of them are high here. But really, on I guess these middle ones, we're taking a lot of points. But then again, it's one of many. This one was also 2019. It's been now almost 5 years. So this kind of area is just progressing tremendously fast, right? But yeah, because it's been a long staple. That's why we're going to look at this today. So how do they formalize the problem setting? Well, actually very simple. They have a predictive model. They call this F hat, right? On some kind of features. Typically these are images, right? So your P would really be some kind of height, width, depth, the RGB or whatever of your image. And then they might look at here this regression task. Obviously, you can also adapt the classification and things like that. And then typically you have label training data, right? So that, I don't know, this is an image of a gorilla, for instance, right? So you have the class. This is given to them, and then what they are trying to get is an explanation model, this FX hat, which has the same input space. So it's also working again on, say, the images, but it's giving you these attributions where the requirement will be that any dimension of the attribution corresponds to one particular feature, right? There are certain features which are less meaningful, for example, pixels, right? I mean, you're going to get attributions for each pixel, but each pixel itself, like how important can it be, right? But that's really the setting they're looking at. That's also holding true for many of these works that you've seen on the last slide, right? That's generally a setting. And what makes this, model agnostic, and they're not even requiring, differentiability for gradients and these things. That's a very big plus. Because, well, they're just trying to train a separate model, actually, right? And we can visualize this intuition very simply in this schematic here, where we have input, model, and output, right? So these 3 columns, essentially. The input is shared, right? So we have these arrows going in there. And then, well, predictive model is what we're given, right? That's the thing that was trained. And then the explanation model is a separate thing, right? And this one gives you the classification, for instance, whereas this one gives you the scores for each of the features, right? Yeah, that's really the setup. And now we want to jump into how they capture causality, right? So again, in quotations, causal objective, in particular for this work, because as you might remember from one of the past lectures, there's something that is called Granger causality, which we have deemed, just like Granger himself, who won the Nobel Prize for this, it's not really causal. It's more like a temporal preceding. Really what it's saying is that, you know, we say that X Granger causes Y if we are really worse off in predicting Y without X, right? So if X is somehow really preceding Y in its computation, that's when we say it's Granger causing, right? And that's what they claim, right? Like they say we use Granger causality, and then it's only in the paper causality, causal, and so on, right? So you got to keep that in mind, right? This is something where I'm like a little bit, should have been nicer to put Granger cause every time, but then again, I can understand if you know, in writing, you don't want to repeat yourself too much. But yeah, key assumptions for this kind of Granger causal setup. We observe all relevant variables, right? Yeah, pretty harsh one, but let's take it. And X temporally precedes Y. How do the authors justify this? Similar to the discussions we had last week with Christian about metrics and about, you know, IRS, the interventional robustness score. He was also questioning, you know, whether it's really a necessity or whether it's something we can just, you know, take for granted in a sense. Similar here. So what the authors essentially say is that you have this predictive model and it's implemented as a computer program, right? And so it will always only use its input as combination, right? Input is exactly defined that way. You know, you give it the image. And the inputs are always inputs, right? So they are preceding the output. That's, again, what defines them as input, right? So what they're saying is, I have a computer program, I give it some input, I get some output, and there is some kind of preceding, right, in terms of computation, right? And the input is also not changing, right? And it's essentially everything which goes into the program, even if that's not the truth of the word, right? And in that sense, I mean, the reasoning is sound, right? But that's what they are working with. These kind of things you got to keep in mind, of course, right? Especially if you're trying to run this yourself. But yeah, so Granger causality is the setup and two very strong assumptions, but which in the sense of a computer program do make sense. So where do they kick off? Now we're going to try to understand algorithmically what's really happening in CXPlay. So they start with computing the error. And how do they compute the error? So they have the predictive model on the image, and that produces labels, say an image of a gorilla and gives you the label gorilla. And now they also do a prediction without feature I, right? In the case of images, there's a lot of those, as we've discussed earlier, right? This could also be superpixel or, you know, groups of pixels, right? However you get them, right? But really, we're just saying we are discarding parts of the image and trying to look at the prediction now, right? And it could also be that we're, you know, maybe deleting the head of the gorilla or the body of the gorilla, right? And trying to look at the prediction now of our model. So these are the predictions without I and with everything. And well, what are design choices? So we were talking about one of them all the time, which is masking essentially, right? And typically it's, you know, zero masking. You're trying to get some kind of neutral value, right? And this is a whole problem of its own, right? Because is zero really a neutral value? You can somehow argue that, you know, semantically, it's not giving you anything new now, right? As long as it's a color, which typically doesn't also naturally appear in the data set, I guess it makes sense. But you can opt also for very different things. You could opt for something like the mean value. Obviously, you can see how this could drastically change the computation, right? Now, we get these predictions. We had done our design choices. Again, like in causality, it's really assumptions. It's important that we just know that we make them. And now we compute these error terms as put in the title, which is really the loss of the model, right? And this could be, you know, MSE for regression or cross entropy for classification. For both of these, right? I mean, you always need some kind of prediction and the ground truth, right? The ground truth we are given, right? Remember, we just have the data set with the labels. So that's how we get the error. Now we want to capture the objective, right? This Granger causal objective. So let's start at the top. We just, you know, define delta epsilon xi as the difference between, you know, taking the whole image and the error we get there from the ground truth and the error we get when the prediction didn't consider some part of the features, in this case, I. You know? Now, this is just, you know, some difference. There's no kind of restrictions on it. That's why we want to normalize it, right, to nicely work in this 0, 1 continuous space. So we get these omega I. These are now our importance scores. These are really the things, you know, like the heat map and kind of things that we've seen earlier. Just for each of the features, I could be any kind of pixel. And what are you doing? Well, you're just taking that delta, so this difference, and just, you know, dividing it by essentially everything else, right? Like the whole constant you get there. Now, these are the importance scores, and let's now understand the Granger causal objective, right? Looks a little bit complicated, but really it's not, right? So up until this point, I think it should be clear. Obviously, we can ask questions any moment again, but really what is happening here, let's dissect this one by one. So we just have this, you know, averaging term here, n is simply the number of samples that we look at, right? So there's n number of images, right, x. We index them by L, so we are looking at images XL, all of them. And now we are looking at two distributions here. That's why you see the KL. KL is, again, a distance measure. It's not a metric, it's not symmetric, but it's a distance measure nonetheless for distributions, right? And yeah, between omega XL and A hat XL, omega XL is really just a collection of these importance scores, so these omega I, right? So looking at the distribution at any I, so you see I just added the I, it's going to be the omega I evaluated on the image XL. And so we just have a collection of all these importance scores. So really, this is just all the importance scores for, say, an image, right? And then A is really everything that our explanation model now predicts, right? And this is going to be the thing whose parameters we are optimizing, right? This is the thing we are learning, yeah? And that's really it. So that's kind of this causal objective now. And again, why is it causal? Because of how we define this, right? Like we take out certain features, and that's kind of in the spirit of Granger, right? We are saying, you know, a feature is Granger causing if without it, we are worse off. And with this kind of objective, we can capture exactly those. So any kind of questions maybe to this setup, or yeah, any thoughts? Yes. So these scores kind of, they are evaluated based on the, if you go back, on the ground truth, right? These Ys here. And so these scores, in a sense, act like a target, right? What we want to have is an explanation model. So for any kind of input, even the ones we have not seen before, we could get an explanation, right? So we got to learn it, and we're using these as targets, and that's why we do it. Yes?
Should we maybe use the absolute value of our W term? Because if our model is...
You mean the omega?
Yes, because if our model is not fully trained yet, we might run into the situation that if we take out a feature, it actually improves our error. So then our value becomes negative, but it still means that the feature that we just masked out is somewhat valuable to predicting the correct answer. But I think it would not. When you take the KL divergence and suddenly the sign is flipped in one area, wouldn't that suggest to this mechanism that we have to that we're still wrong?
Yeah.
even though that feature is valuable in predicting.
I think this is a super interesting and valid thought, right? I think what we would have to do now is really just, you know, write down a little bit, maybe on an example, simple example, the maths, right? To see what happens in these cases, right? Where essentially we don't realize that our predictive model is not perfect yet, or in any sense. Maybe it's already handled in this setting. I could also imagine at least one scenario. But yeah, off the top of my head, I couldn't do this now. I think that's the only strategy maybe to answer this. But interesting thought. Exactly these kind of things are, I think, how you at least do an incremental improvement over a paper like this, right? This could be a master thesis, right? Like looking at this, evaluating these kind of setups, right? And then seeing, oh, this actually they didn't think of, right? For maybe good or wrong reasons, right? And then pick up there, improve that, and boom, you're already better than what was there before, right? Yeah, interesting thought. Yes. So here it's really about the explanations. So we don't even care. We just assume that's why it was written, given. We just have the model, right? Yeah. Someone gave us, right? But obviously, you know, in any kind of typical pipeline or something, what you can imagine is, well, if you're the one who's trying to do the whole ML, obviously you're first training your model and then you're trying to explain it, right? So you then try training the explanation model. If you Well, no one is telling you how well you trained your model in the first place, right? That's the thing, yeah. Okay, cool. Then let's look at some examples, right? After all these images, so we should look at images, and that's always nice because images convey a lot of information. So what we can see here now, again, 3 columns. On the left, we have kind of the source image. Then we have the mask, which is really generated by our attributions. It's really just the attributions, right? And then the masked image, if we use the mask on the source image. And what you can see, obviously, here on the left is the MNIST number 8, right? And what this task is now about is trying to mask, you know, the features which would turn an 8 into a 3. Quite, you know, intriguing and interesting task, I'd say. And now over the columns, we just see these different methods, right? These competitors, deep, sharp, sharp, line, and see explain now with a UNet architecture trained, right? And what we can see really is, well, I guess you would agree. I certainly would see myself that, yeah, I think these images are convincing in the sense that the top one here resembles most of a tree, right? So really you can see the mass is kind of focusing on the left-hand side of these circles of the 8 and just removing those. It gets a little bit wrong in the middle part, so disconnecting it, but all of them actually disconnect. And I mean, the further we go down, the worse, the more noisy it seems to be getting, right? But that's really what's happening, right? So we trained our explanation model, in this case with the UNet architecture, using the approach we've just, you know, sketched out. And now we can do this kind of thing. And I think that's pretty cool. Also, if we look at another example, so, you know, the question is this a gorilla or a zebra? Same kind of setup, just have one competitor out. Don't ask me why. But we can see that, you know, it's a little bit difficult to see because the gorilla is anyhow mostly blackish. But you can see that the attribution map for C-explain is really centered around the gorilla, right? I don't remember any more the details regarding the zebra, right? Why that was, you know, a point. But really the important thing here to remember is, I mean, this is just a natural image now. This is not about masking and changing classes like before in that sense, but it's really focusing on the semantically more meaningful aspects of the image, right? In this case, the gorilla body, right? Okay, so we have seen now essentially how they define causality in terms of grandeur, how they define explanations in terms of feature importance, and 2 examples of, you know, really running this. As a final note on this particular work, I would just, you know, point to the code, !code, because, you know, code is not just available, it's actually working and it's nicely curated, right? And I think that, you know, boosts a lot of, you know, the popularity of any given paper which proposes a certain method. It's a Python code base. You can easily even install this via pip. They have even some nice Jupyter notebooks where, you know, you can run these kind of settings. I mean, you know, this looks pixelated, but it's just a little bit scaled. Typically, there's a lot of these data sets with very small images, right? But I guess this is a dog, right? And, you know, these are the kind of things you get, right? The attribution map. And they also talk about uncertainty. We didn't do this now because this is not as important to us. We are more on the causal side of things, the conceptual side of things. But that was also an integral part of the work. It's not just that, you know, they proposed this Granger-esque objective and ran some things and, it, you know, no, I mean, they really had quite extensive study of this topic. But talking about code, right? Let's return to some XKCDs. This one is on code quality. It starts again on the left. We have 2 colleagues. One of them has written a code, it seems, right? And saying, keep in mind that I'm self-taught, so my code may be a little messy, at least, you know, very self-conscious. I think actually most, you know, PhD students will find to be exactly that way. And then, you know, let me see, I'm sure it's fine, right? And then, wow, This is like being in a house built by a child using nothing but a hatchet and a picture of a house. It's like a salad recipe written by a corporate lawyer using a phone autocorrect that only knew Excel formulas. It's like someone took a transcript of a couple arguing at IKEA and made random edits until completed without errors. Okay, I'll read a style guide. So you know, bashing the people, yeah. But I guess everyone who's written code knows that, you know, there's elegant code and then there's code. And yeah, that's kind of the setup. But this code, she explained, it's really awesome, right? We got to give the credit where they're due. Okay, anything else for C explain, or are we ready to move to the next one? Yes.
Because when we train this model to get to generate those important weights, well, we can still compute them and on new images, because well, is it faster? Because I don't see any other.
Yeah, that's a good point. Let's think about it for a second, because I think this is one of the more important ones. So let's think of images maybe, yeah. There we have pixels, right? And let's say we have like 1,000 by 1,000, right? Which is not that big of an image, right? It might be bigger than your typical data set, but then, you know, you already have 1,000,000 pixels, right? And now think of just one pixel is not that important, right? So think of all the power set essentially of that set, right? Just for one image. It's super large, right? I think that's really the issue. It doesn't scale. Yeah. Because otherwise, of course, you could just go ahead and take for new images, right? Because that was, I guess, the key motivation, right? For new stuff and having a function which really learns this. Yeah.
Do you usually really use only one pixel or window-based approach? Because as you say, one pixel seems awfully small and insignificant.
No, I think people do, you know, I think typically it's window-based approach. I think so too, right? Maybe they have different levels of filters or stuff like that, right? Or they downsample an image and then go there maybe on a pixel level, right? But sure, there's many ways, but that's computer vision.
Yeah,
yes.
Exactly.
But then again, right, you're changing potentially the semantics of the image by discarding important details and stuff like that, right? Like if for a zebra it's important to have the stripes, and he'll downsample so much that you don't really see them anymore, or the signal is very weak, right? Then it doesn't work anymore. Yeah. Okay, cool. Then yeah, in the interest of time, let's move on to our second work of the day by a single author, Sander Beckers, a friend of mine, amazing guy. He's a philosopher actually by training, and he has talked about, well, he does a lot of analytical philosophy, so grounding, you know, things really in the framework and going from there. And you know, the things we've seen with Halpern. So he used to work actually with Joseph Halpern himself, so he knows all the craze about actual causation. He's one of the few really strong experts on this. And well, he also tackled explanations from a causal standpoint, because causality is what he does, right? And XAI, because, well, AI is becoming ever so important. And this was published at CLEAR 2022. CLEAR is kind of a new conference which started in that very year, which is really concerned with learning and reasoning, right? It's still a small conference, but, you know, appreciating the fact that, you know, this area of causality or causal AI, however you want to call it, is really becoming more and more important, more and more mainstream, and less befitting of classical conference venues such as NeurIPS and so on, although obviously people regularly publish there as well, just as we do. Yeah, there was this movement creating a new conference essentially, right? I think that's really how it happens. Similar thing happened very successfully for people in geometric deep learning, where they look at, you know, graph inference and things like that. But yeah, causal explanations in XAI, as I was already hinting to with this little introduction of mine, this is going to be a purely analytical philosophical work. So we're not going to see any images now. It's all going to be text, but we're going to imagine these things and try to go through it step by step. There's a lot of formulas, so I try to condense this to the more important parts. Yeah, I know this part might be a little bit daunting, but I mean, it's really clean and beautiful for what it is. So yeah, without further ado, let's jump in. example. So here it's the best to kick off with an example. So let's really go step by step so everyone is on board and that we visualize this somehow, right? Because I think it makes it easier, right? So we are in the setting of a loan application, right? So you're someone, you're trying to get a loan at a bank, right? Say, I don't know, you want to buy a car, you want to buy a house, whatever, right? I mean, nowadays people might not want to do that because of all the other reasons not to, right? It's getting a bit more difficult, but imagine your parents maybe or whatever, right? And so, yeah, consider now a system of loan applications. So we are saying that this is being done algorithmically, right? So the bank, you know, has a certain system of how they want to do it, right? And it's actually captured by a causal model, right? So we know what the computations are, what the variables are. And so what is it? Well, y is going to be the variable, the random variable representing whether, you know, an applicant gets a loan or not, right? So whether you get the money or not. And y is being computed, it's being caused by x1 and x2 essentially. X1 is going to be the applicant's income, you know, measured in dollars, euros, whatever you want, right? And that is going to be summed up with 5 times x2. X2 is going to be the applicant's savings, right? So whatever, whether it's on that bank, some other bank, whatever, somehow the savings that person has accumulated of sometimes. Don't ask me where this 5 comes from or anything. The author, you know, chose to set up in this particular way so he could, you know, play with some nice numbers, I guess, and make it somewhat reasonable. And then minus this 225,000, I think, you know, one interpretation I might maybe have here right now is that, you know, these are the applicant savings, right? And since we are checking whether this whole quantity is going to be greater than 0, if you have, you know, large savings, you know, which maybe be larger than 225,000, with this 5 times factor, then you know, you should be granted a loan, right? Obviously, because if shit goes down, you can still pay the bank, right? That's kind of the setup, right? Similarly, why do we just take x1 here? Obviously, if you're making a lot of money, which can, you know, compensate for this, even if you have low savings, right? You should also get it, right? Because again, if shit goes down, they just, you know, get whatever you have, right? So yeah, I guess we can conclude kind of that this is reasonable. We are looking at these two numbers and checking if it's greater than 0. Actually, it's a bit more complicated. So really, this is computed by x1 and x3 because x3 is the initial deposit. So what you put to the bank or whatever at first, right? How you kind of go about getting that loan. And this thing, it calls it computes x2, right? So that's the thing. We just have this additional structural equation here where we're saying 3/10 times, you know, the income of the person plus that initial deposit, right? That's going to be how, you know, you generally get your savings, right? Given that x1 is going to be yearly income, right? Say 50K or something, then it's going to be, you know, 3/10 of that, right? So 30% essentially. And that just summed with whatever you do as an initial deposit to that bank or something, of what you had before maybe or something. Kind of seems reasonable as an approximation maybe to what savings typically are, right? Obviously, if you're trying to counteract these examples, you can go exactly into these kind of settings and propose an alternative, right? But then again, we are just trying not to get an accurate, you know, system of loan applications right now, just trying to get an example where we can conceptually distinct concepts that are important to us, right? And here it's going to be about explanations, but that's down the road. First of all, we are going to talk about sufficiency and things like that. But yeah, so we have y. Simply, you know, if this quantity is greater than 0, then the person gets a loan. It's dependent on income, about savings. Savings depend on income and initial deposit. And there's then a final equation which does not play a role in y. It's x4. It's like the safety deposit box, right? Imagine there's this, you know, room, maybe underground in the bank, where you have your little, you know, safety deposit box. And it's indicating whether, you know, someone is taking them out or not, right? To get the loan. And typically, you know, we compute x4 simply as whether, you know, this relation is satisfied. So whether the savings are more than $1 million. So if someone has more than $1 million in savings, they're just going to take out from the safety deposit box. Also seems to make sense. Good. So this is kind of the setup we're imagining, right? Someone is trying to get a loan and there's these different factors, right, we typically know of. Now, if we continue this example, we are going to start right away with machine learning, we're going to say that a model is very much capable of picking up that anyone who takes out a safety deposit also gets a loan, right? So if you go back to the equations, you can really verify for yourself. Every time this is 1 naturally occurring, savings must be greater than 1 million, right? And well, if savings are greater than 1 million, you can play the game here. You're gonna get the loan, right? Y is gonna evaluate to 1. So on an observational level, really, the ML model is just looking at people, who have, who are taking out deposit box, because again, it's like the, what we're seeing before with the watermark or the label of the photographer or something. It's just like a shortcut for learning, right? It's a surefire way of doing the right prediction really quickly. Good. But well, I guess here I'm just writing it down technically. So what you can see is H is going to be the ML model. It's just the function that we have learned, right? Remember, generally, if you talk about neural nets or something, they have this architecture, inputs, outputs, these activations, and so on. But really, it's just a function they're approximating, right? And the machine learning model would just learn this kind of function, right? Where it's just, as soon as it sees that, safety deposit is 1, it's just going to return 1, right? And independent of any other inputs you give it, right? And well, that works in this particular case, because again, as we have just seen now, if you look in the SCM, then our SCM-M, which was the thing we just presented previously, satisfies that x4 equals 1 implies y equals 1, right? If someone takes it out, then that implies that they're getting the loan. Now, let's look at this from a causal perspective. And now in the really Perlian sense or Halpern sense as we know it, right? Talking about interventions and these kinds of things. Well, although the safety deposit box has served us very, very well right now, right? And was a surefire way for the model to know, it would be really absurd to recommend someone to, in order to get a loan, to just go there and take money out, right? It kind of doesn't make sense. I mean, it depends how much money you have there, right? So, interestingly, doing that is also not even necessary, right? So, if we look at the model, then we see this property being satisfied. So we see that our SCM-M does not satisfy, right? Does not model that y is equal to 1 if x4 was set to 1. Again, what does this x4 set to 1? It's our do intervention, do x4 equals 1. What does it here mean? Just saying someone, well, go now and take out your deposit, right? If someone does that, right, it doesn't matter, right, how much money they have. They're just going there and taking the deposit, right? And in that world, y is not necessarily 1. It can be. I mean, if you tell it someone who has more than 1 million, right, it would have occurred anyways, right? But someone who doesn't have, for those it won't work, right? And that's what we are seeing here, right? That's also just what's being described here. There exists some exogenous term u, right? Again, the u would be, a particular person, right? Who has particular, instantiation of these values. Now, interestingly as well, we can use interventions to do good recommendations, right? So we shouldn't recommend someone to, go get their safety box, because unlike the ML model, we know that that is not the cause, the thing that makes it work. We could just recommend someone to increase their savings beyond 45,000. So if we set 45x2, the savings to 45,001, then y is going to be 1 in the SCM, right? So that works, right? Like if someone were given 45,001 say dollars, then they would definitely get the loan. And that's because that's how the system works. That's where the computer switches, right? That's where the decision boundary essentially is, right? And that would really work. The other thing obviously would not work, because again, if you again imagine we want to do this intervention x4 to 1 and check whether y is 1. Well, set this to 1, ignoring x2 and all this condition. Just set this to 1, and now look at y the computation. Well, it doesn't matter. There is no x4 in here, right? But now, if we consider this one, where we're setting the savings to 45,001 and look at y1, well, savings are part of the computation. If you do the maths, you're going to see you're going to end up in the positive case. So that's really what's happening in this example, right? So any points, any questions, impressions, thoughts here? That's really this analytical philosophical style that we are approaching, right? So we are looking at examples, We're trying to find real-world equivalents. We are approximating them just enough to get our concept straight, but we are doing so rigorously, right? So really taking the formulas and details, right? Anyone has anything against, this loan application system, something that doesn't make sense? Again, it's not really about the specifics of the loan application, right? But is there a mistake or something? Should we? Okay, if not, well, I was not able to find one either, and I was actually very happy with this example. So let's just keep going and capture now these characteristics, because after all, this was an example, but trying to capture something important, underlying. And these are the concepts of sufficiency. More specifically, Sander distinguished between Greek and direct sufficiency. Sufficiency in the sense of how we have it here in the first bullet. So different notions, mathematical notions of how one state of a variable, right, x being equal to x, a little x, right, is sufficient for the state of another, y being equal to little y. And now weak sufficiency is said to be happening in M for x and y in these states if for all the exogenous terms, and the RU is simply the range of the exogenous terms. So it's all the values it can take, right? So that for all the values you could ever take, in combination with that M then, that M would model this causal effect, right? That intervening on X would see you Y being little y. That's what it's saying with weakly sufficient, right? So you intervene on X with that little value, right? You see Y being Y. For all the U's that you compare with your SEM, then you say weak sufficiency is satisfied. Now, direct sufficiency is just slightly more complicated, but also very intuitive. Very same structure here, just with the direct. But now we have the C element of all the values that C could take. And how is C defined? C is simply all the other variables except for X and Y, right? So everything else we haven't considered. And then additionally, for all the U, that we have this condition, right? So we are just extending. So what this is saying essentially is we are making our approach immune in a sense to interventions on other variables, right? We're really trying to capture the causal effect only from X to Y. This is very similar to kind of the IRS technique that we have seen last week in the metrics. So let's make this a bit more clear with the example. So in this case, for the loan application, let's return to that one. So if you know that the savings of a person are 45,001, then this is both weakly and directly sufficient for y equals 1. We can verify this easily, right? So you go back, right? You imagine now, okay, for all the use that I could take, if I intervene, and you're going to see that indeed this is the case. And now here additionally, for all the other variables and all the interventions I could do there, would it work? You would also see that's the case. I'm not going to play this through now, but you could verify this. However, interestingly, for this loan application example, if you consider now this here, right? So the income to be 50,000 and the initial deposit to be half of that, then this would only satisfy weak sufficiency, but not direct sufficiency for the observation y equals 1. Now, we have two notions of sufficiency that somehow talk about, how intervening on certain parts with certain restrictions will, affect what we are seeing. When is it really, sufficient? And we might ask the question, okay, which of the notions is better, right? That's the game we are always playing, right? We're trying to capture the actual notion, which is underlying reality, or at least which is maybe most useful to us, right? And so we can compare them, obviously, because some of them will satisfy some cases and not, right? And generally, you can say that direct sufficiency is a better thing. And why is that so? Because we can imagine a following situation, which we would like to have satisfied. And what is that situation? So imagine that an applicant with this income, 50,000, and also, this initial deposit of 25,000, is told that this suffices for a loan, right? Because if you do the maths, it works, right? Like you can get a loan with this, right? However, now as a reaction, obviously, they're saying, oh, yeah, I'm safe. The applicant concludes, that having high savings now is not needed, right? Because my deposit and so on was good. So they are just spending now 20K of their savings, right? But as we remember, right, from the original formula, the savings are an integral part for getting the loan. And now this would lead to the loan application failing, right? And that would be a shame, right? That's something we don't want to cover. And if we were to use weak sufficiency only, then we could not cope with this case. That's really what we are saying, right? So we have played this example, we have kind of generalized the notion, we have captured it formally, and now we're seeing that, well, some of these notions are weaker than others because they just cover less examples, right? Now, this is going to be the more difficult part, right? In the sense that, you know, this is a very dense paper as well, and you really have to work through it. But I'm trying to you know, massage it to make it easier for you. But really, they are now generalizing then this, right? So yeah, this you know, direct sufficiency is kind of a cool thing, but this direct sufficiency is immune to the, I mean, the cool thing about it is that it's immune to the influence of interventions on other variables, right? Because you consider them in the formalism, right? So if we go back here, then you can see that we are looking at all the other variables except for x and y and intervening on those, right? That's what the bracket notation here means. So we are immune essentially to that, right? Meaning that, well, we consider those. However, we don't consider which variables need to be shielded by which, right? Not all of them that you could intervene upon are important for what you're considering. And that's why Sander essentially just proposes this notion of strong sufficiency. Again, it's the same structure, but now we just have this additional set n. This cannot be any set, you know, this is constrained really by this definition that, you know, n is really a superset, potential superset of y. And we have that x is, when it's equal to little x, is directly sufficient for n equaling to little n. And then, you know, these values, again, they are a potential superset as well. So in a sense, we are just introducing this other set, which can be larger, and x needs to be directly sufficient for those. That's what he calls strong sufficiency, and it's a kind of generalization of what we have seen before. Now, bear in mind, we're not playing this example through here. Actually, there's some more coming up. That's why I'm saying it's a bit more difficult part. So just take this, I guess, as how they go on about, you know, defining these things, generalizing these things, refining those things. You can see that structurally speaking, again, if we were to take like this category theory approach, right, it's very similar. But why did we need this? Because that's actually how we define our explanations. As you can see, it's also a bit convoluted, right? Like we have these layers of definitions, but the explanations we can now very easily define at least, right? So what we are just saying is, before in C-explain, explanations were just these feature importances, right? They were just, you know, these little heat maps essentially. That's an explanation, right? Here, an explanation is this pair here. It's the state of a certain variable, and then the set n. Not even the state of that n, just the set n. And we say that this pair is a sufficient explanation. It's an explanation, but it's a sufficient one of y equals to little y, your observation that you want to explain, if x being little x is strongly sufficient for y equal to little y along n. And remember, that's what we just generalized here from direct sufficiency. And for direct sufficiency, we had this example here, which we could make a little bit sense of to get at least some intuition on this, right? Really, if you really want to appreciate this, you have to dig a little bit deeper into this. Now, there's again, as everything, there's, you know, different shades, right? And so we can talk about an actual sufficient explanation, or we can talk about a direct sufficient explanation. And really, if these properties, either of them is satisfied, right? So if our model for some exogenous instantiation U is modeling this explanation component, then it's an actual sufficient explanation. And if n is equal and not, you know, a superset of y, then we say it's a direct sufficient explanation. But that's really what's happening. So we see here, we have a drastically different notion of causality because we are using, well, now again, Pearl, Halpern, classical causality, not Granger causality. and we also have a very different notion of an explanation, right? What we're saying here is that an explanation is really just this tuple, right? So there's a situation. This is what you're trying to explain. This we could say is similar. It's maybe a class like, why is this an 8? Why are we seeing our neural net predicting an 8? And now this is a pair. Now it will be all the features maybe, you know, that serve to classify this as an 8, right? So in that sense, we can again map this, and it seems to be a sensible interpretation of the word explanation or what it should be. And I guess we could go ahead and somehow apply this as well to what we've seen previously. But itself, it's a very different way of defining the explanation per se, right? Because in the other thing, we had this model and it just produced these values, attribution values. Here, we are really looking at something which actually exists in that sense, right? So, yeah. Yeah.
So, and here is a set of possible outcomes.
I actually would have to go back myself and see what n is exactly. Yeah, I'm not sure myself. Yeah. When you say possible outcomes, what do you mean by possible outcomes?
So in the last line, for example, we repeatedly draw relations between y and n. So set relationships between them. So I would imagine that they're at least part of the same superset. So then n would contain stuff that can be in y. So that for me would lead to the conclusion that somehow n is a set of possible outcomes, but I wasn't sure. So that's what I wanted to ask. But
don't forget.
Y is the superset.
Don't forget, right, that y in this case could be, you know, just y itself could be your, say, classification, and then little y's would be the different potential outcomes, right? However, n would now imply that there could be a variable z, which is also additionally measured, right? Which could be a completely different property now, right? I cannot think of one now off the top of my head, right? But y itself and the little different values for little y, these would be, you know, cat, dog, and so on and so forth in our previous example.
All the variables, the set of things, sets, switches we can flip, for example, states we can track.
So if we say that, for example, our SCM, or let's say here, we go back to our setting of here, then essentially we have X could be, you know, just we know about the applicant's income, for example, and we want to argue whether, you know, this is now a strong sufficiency for, you know, Y being equal to 1, someone having an income, right? And now N should be something which contains Y and possibly more. So it could be also, say, the initial deposit, right? And so what we're then saying is that X being, say the income being 50,000 is strongly sufficient for Y being equal to 1. So the person getting the income along N, which contains in this case both the loan outcome and say the initial deposit, if X, so the income being 50,000 is also directly sufficient for N, so both the loan being granted and, you know, the deposit being in a certain value. And now you would go back to direct sufficiency, right, and see when this is the case. We had to play. I couldn't build up the intuition now, right? But you see how we're doing it, right? And you see what kind of variables are components of it, right? So essentially, from all the variables, it's a potential superset of Y, and essentially X somehow needs to be directly sufficient for that N, right? Such that we can say it's strongly sufficient that for Y only, right? Along N in this case, because N there could be multiple N. Okay, so but yeah, as you can see, we are playing this, you know, rigorous drill here. But yeah, this is essentially explanations, and the cool thing is really in terms of sufficiency, you can really just define it then, yeah. And there's a clear distinction of what its components are. What you can also talk about then is the goodness of an explanation, right? So you can say that well, there might be multiple explanations to begin with, and then some of them might be more important than others, or more better than others, right? I mean, everyone knows, I mean, I'm just making a real world analog without drawing any connections here now, but you know, you talk to someone and then, you know, two people explain to you, but you understand the other person for whatever reason better. Could be just because of communication, but also could be because the actual explanation is somehow better. Yeah. Here we just take a very Occam's razor type of approach, I guess. We're just saying an actual sufficient explanation is good if it's simply the smallest, right? Like the paradigm we are having here is an explanation should be as concise as possible, right? There shouldn't be redundant parts. So it should be minimal, technically speaking, for both X and N, right? This I've already, I mean, in the paper, you'll see a very different way. It's a lot more formal, right? But really that's the essence. So I put it here, as we have seen already enough formulas, I guess, from all the different notions of sufficiency. Now, interestingly, I guess we get to the first kind of main result, the first theorem. There is a fallacy that we recognize immediately in machine learning models. And it's actually a big topic here. It's the essential topic of their work in particular, right? So if you consider, say, the IID assumptions on, the samples of your features, right? Like what do we typically do, right? Like we have, I don't know, the feature, we have a certain image and there's certain samples, right? But we say the images themselves, they are, independent, but they all say follow the same distribution. They're all images of cats or so. Then we have this notion of independence. But then generally, we can also just have an independence of the features themselves in the sense that they don't interact, right? Like say we are talking about the disentanglement setting from last time, right? And there, you had shape, you had weight, you had size, right? And these things don't interact with each other, right? They're independent factors of variation. And these are things we encounter a lot in machine learning and all kinds of guises, right? And really what the author here can do now with these notions that we've introduced is figure out that there's a collapse of sufficiency when you have this independence. Again, which is typical in our machine learning models. So what happens is that weak sufficiency is equal to direct sufficiency is equal to strong sufficiency. But as we've seen in our examples, they are not, right? Like we have these examples that they are not the same, right? One of them is always stronger actually than the other. But in machine learning, they're all the same. And that's not good. And it happens because of this independence assumption, right? So really, we can already conclude by this. It's kind of a very strong and harsh critique on machine learning because it's a different way of saying non-causal ML doesn't work. And in this case, for explanations. And so it's a punch in the face for XAI in a sense. Interestingly, though, there's also a downfall of causality, it seems, because there's two more theorems in this work that you'll find, which relate again to this independence. And they also lead to collapse. They lead to collapse on counterfactual dependence and causation itself. So what do I mean? Let's illustrate this on causation. So you remember maybe from the little stint we had on actual causation. It's different from type causation, from Perlian causation, in that sense that we don't talk about, does smoking cause, lung disease or something? We are talking about, particular individuals, about the U-terms, right? Like if I take the aspirin now, will my headache go away, right? If you take a aspirin, maybe it doesn't go away, right? So that's kind of the distinction on a high level between, actual causation and say Perlian causation. And now when we say collapse on the level of causation, all of these things become equivalent because of the notion of independence. And that's the interesting part. So saying that, X being little x, so having an image of a gorilla, say, is a direct cause of Y being little y, say, the network actually classifying it as a gorilla in our SEM, or agreeing with our SEM, it would be equivalent to saying that X, well, this gorilla image, or that there exists some kind of instantiation actually of X, which is an actual cause of Y, which is equivalent then again to saying that it's part of a good sufficient explanation of this classification. All of these things collapse essentially. And to be quite frank, I have not thought myself further than, everyone has to do this, right, and priorities. So I think there's a very deep result. I would love to go back into the proof and really dissect step by step. Not going to do this here today, just trying to show it. But I think there's a lot to read out of this result. As we have seen just one slide before, sufficiencies collapses, and we have seen that these different notions of sufficiency are indeed different, right? We can have different examples which work for one and not for the other, and important examples. And now we have the same for both counterfactual dependence and causation, here showing causation, because we know that a direct cause is not necessarily an actual cause. And who's saying that these things need to necessarily be also in the explanation, right? So, but all of them become equivalent. And that's just because of independence. So independence is an oversimplifying assumption, essentially, right? And it might be already in some way integral, right? If we consider something like IID satisfying this notion of independence. So maybe to ease up a little bit the mood now and to, make this easygoing and finish on a nice note, I have this one for you. So I think it's kind of quite ironic that I have to give you this thorough explanation for a paper that really tries to explain what an explanation is, right? It's very circular, yeah? And as you can see, I ran out of explicitity, so I started making my own. I hope I made a good one. Well, yeah, to keep maybe on that note, I'm sure all of you have a lot of thoughts, maybe also confusing and conflicting thoughts on these kind of actual causation related topics. They are super dense, but they are precise. One really has to study them to appreciate them much. And I'm also not that where I want to be, at least on my personal level. But yeah, anything I want to talk about in this particular reference, this would be, yeah.
It's kind of arbitrary in the sense that with weak sufficiency, we model our stuff with respect to variables we expect. With strong sufficiency, we also consider stuff we know about but don't expect. But this is fundamentally limited by our horizon. So when I imagine, for example, AI researchers running into walls because just like we had in the beginning, there's information in the data set that no one thought about, no one expected, right? We can't, in this case, really say that something is strongly sufficient because this is limited by what we expect is relevant, even though it isn't fundamentally. That we can't know what actually, we can't know all the things that really are important. So it becomes kind of a border around our mental horizon, what we think we know is actually important.
So I was just wondering whether you might be confusing with the previous one where we talked about C-explain, where part of Granger is assuming that we know all variables. Here let's see whether this is, or whether I'm confusing. Let's see whether we actually need this. So let's see weak sufficiency. What we need is, well, we are looking for some kind of a thing which is sufficient. So, we are looking for the x's, okay? Y is the thing that is given to us. That's what we are looking for. M we typically don't have. And here, this is the interesting part, because we can say that we might have some approximation of M or some belief about M. Let's say it's the right one, then we can go with this. Usually it's not. So we would still make, I guess, an explanation or a correct statement of sufficiency, a sound reasoning, just with the wrong model, right? And that's an independent problem in a sense, right? Like, I can give you explanations, which are good explanations in that sense, but which are wrong because my model is wrong, right? But the mechanism of generating the explanations from my models was right.
Yeah.
Right. But yeah, so okay, and now for all use, this we can, if we assume, well, obviously, let's assume we have some kind of SCM model. So we also have some assumptions about the use. So we can also check that. We would just check over all these distributions whether it's satisfied. So yeah, technically we can quantify this. And now your question was regarding, here we don't have anything about all relevant variables.
Well,
that's a property of M, right?
If we would include C in our R from the definition for weak sufficiency, we're limited to weak sufficiency because all of the other stuff we know about, which is big C, would be already contained in our R stuff we're already tracking.
Okay, let's take this offline. I think this is a more involved discussion. But yeah, what we can say definitely is that, the SEM, obviously, here we talk about in principle, about sound reasoning. Doesn't matter whether the SEM is true or not, or whether that such thing exists in the first place, right? And so in that sense, we are safe at least. But yeah, okay. Anyone else? You can also comment on my XKCD mimicking skills. I mean, yeah.
Actual explanation.
Yeah. So I'm not aware of any implementation as of yet of this setup. I think at least for these simple examples, well, obviously it's doable because we can play them with the examples, right? So we can write some algorithm for it, how it scales, right? Like where the limitations, so on. This we don't know about. Of course, I think that's just a natural next step. And again, I think what saves us here in comparison to, say, causal discovery or something is that we are not too much focused on having the right SCM. Because again, the explanation generator mechanism is an independent component, and we can somehow get closer to the right one there and just have it fixed, right? So yeah, but nothing, unfortunately, yet. Maybe Sander has it hidden somewhere, but I would have to ask him. Yes. Mm-hmm. No, yeah, it's more specific. So it's essentially what the author does is they take an ML model as being a function approximator, which predicts from some set of exogenous variables the features to the whatever kind of output space you want to consider, say a single classification label or whatever. And these exogenous terms, so I was questioning this a little bit myself because, typically in machine learning, we have features which have names, and exogenous terms are usually the things that don't have names, right? Everything else we forgot. But maybe we can think of it as some kind of intermediate representation that the model uses to predict or whatever. And independence there, right? That these ones are not talking to each other, right? That's how it's defined. And as far as I've concerned, the way I've captured this is, in machine learning, typically through IID or, independence on exactly, when the features cannot talk to each other in a representation learning setting. Whether there might be more machine learning-y notions that capture exactly what he means by that kind of independence, that would be very interesting to know because, well, these are very strong results, essentially, pointing to independence, right? But yeah, actually in that work, you also see, I think pretty much always independence is capitalized and it's written in bold to highlight, but that's the thing. Okay, cool. Then the last 20 minutes we are just going to use now to go, well, over one of my works. Yeah, there's an ongoing project. Yeah, together with Dave, who's a professor in Eindhoven, Konstantin Rotkopf, who's a cognitive science professor here in TU Darmstadt, and Christian Kesselberg, my advisor. And well, we changed the title a couple of times because sometimes you also got to change the title to leave a different impression. Sometimes people are just so stuck up about the title, it's almost weird. Yeah, but yeah, we just went for the straight thing. We just called it generating explanations from linear SCMs because that's really what we do. Yeah, so let's start with an example again, and I think now we are gonna pick up the mood again for Friday and for the weekend and everything, because we're gonna have a lot more images, even more than we had in CXplain now, because I'm gonna propose to you a drastically different way again of thinking about explanations. Again, different notions of explanations, different notion of causality. Here we're gonna take again the Perlian causality view, but less Halper. And we are gonna take an explanation point of view which has nothing to do with feature importance or just giving me a set of variables, right? One which I find personally a lot more compelling and a lot more reasonable for the average person, I'd say. But yeah, let's before I let me stop selling you this thing now and let me just introduce you this thing. Yeah. Raban actually knows about this, so you can just, you know, do whatever you want. And
You're the expert though.
sure, sure. And yeah, so the running example is the following. So let's, you know, consider a medical setting. We have, you know, patients, and we're recording some kind of features of interest on their data. And, you know, these will be health-related characteristics, right? So they capture things like the age of a person, the nutrition, the overall state of health, say, and maybe how mobile they are, yeah? And we capture them numerically in a semantically meaningful way. What does that mean? So age can, you know, be typically, you know, it could be the integer that we're using. Here, I'm just using the continuous scale. So, you know, just map your, you know, every day of life somehow to this number. Nutrition could be something like the higher the number, the more balanced the food habits, the overall diet of that person is, right? Health, again, could be some kind of, say, summarizing variable, the overall state of well-being, right? How does the person feel? Maybe a kind of a scale report of how they feel themselves. And mobility would be something, again, like, you know, is someone in a wheelchair? Is someone maybe just, you know, in a kind of population average setting? Is someone really, I don't know, athletic and can do all kinds of, you know, spider snaky kind of things, yeah? So that's really the thing, right? And so if we have a given patient, say Hans, then we could have, for example, these 4 values, right? We could see that, you know, well, age is quite high, it's 33 years old, right? Then we can see these numbers, at least in comparison to those, are low, but we are getting to the comparison in a moment, right? But that's really just the running example we're taking on. And now what I want to introduce is a reasonable question one might want to ask, right? So say we collect statistics now on a population, right? Again, Hans is just one of many patients, right, in the pool. And we can obviously collect information on, you know, say average health value or say average mobility or something, right? We can see, you know, maybe our sample has mostly young people, so the average age is going to be skewed not 93, but might be maybe 35 or something. Yeah. Well, if we have these kind of statistics about a population, that's a reference point, kind of anchor. And this thing can be used actually to define a question, a reasonable question, as I propose, right? I call these things why questions. So we remember Hans has a mobility of 26.2. Doesn't mean much as of that, right? We just know that, you know, higher mobility means someone is very flexible, mobile, whatever. Lower mobility means they are, yeah, well, bound to some devices. And now we know the average mobility in the population is 35.6. We clearly see that this is below average, right? Well, we don't know now how, you know, this accelerates, right? So we might say, oh, this could be close or anything, but just take for now as face value, this is lower, right? So it's definitely kind of worse off than the average in the population, right? Or an average member of the population. Obviously, you could go ahead and, you know, you can just take the empirical mean, but then, you know, you might be sensitive to outliers, so you can use the median, right, to be more robust, right? You could still define the same thing here. And I would argue that, you know, typically you would call this, or you would formulate this question then as, well, why is Hans' mobility bad, right? So I'm seeing that, you know, the average state of well-being in the whole group that I'm looking at, all my different patients is like that. And now Hans is the odd one out, is worse off, right? So I could ask myself, why is Hans in such a state, right? And I'm referencing obviously everything else that we measure and know of, right? Age, health, and so on. Now, I'm looping back actually to the first work that we've seen today, C-explain, because, well, we can also evaluate C-explain on a setting like this. I mean, it typically doesn't use your SEM in that kind of way. Well, that's a shortcoming of its own, maybe. But really, the medical doctor can ask this question, why is Hans' mobility bad? And then say, use something ready available like C-explain. And I would argue that there's, well, a couple of shortcomings. Although it's an amazing work, which does amazing things, I'd say that there's no information on structure, right? So again, this is just, I guess, in the whole setup of its own, right? I mean, they're using Granger causality, right? So, but then again, it's a causal explanation, right? So that's how I'm judging a little bit. And, you know, no information on structure, then translated into the setup means something like, you know, we cannot tell whether health is a direct effect, and whether nutrition, for example, is an indirect effect, which is mediated by health. What we really get is just, again, these numbers, right? So we have our three features, except for mobility, right? Age, nutrition, health, which should serve as the explanation. And now they just get some kind of importance scores here measured in percent, right? We see age as highest, then nutrition, then health. All of them are positive, right? No information on structure. Furthermore, there's no information of the causal effect in that sense, right? At least the sign of it. So no causal effect in general, because again, it's Granger causal, but no sign as well, because, well, age, arguably, if you make someone older, they're not going to be healthier. It's going to deteriorate, right? On the other hand, you know, if someone has a better diet, generally that has a positive effect, right? These things are somehow not reflected here, right? We just see that age is somehow the most important. We might agree with this, but we don't know in which way. And nutrition is then the second, and health is the third. Here on the bottom, we have two more properties, which I call non-smooth and determinism, which might not be amazing, right? If we think of Pearl's framework, such as you know, structural causal models, then exogenous variables are really at the center of this counterfactual theory of causation. And if you have determinism, well, you're not having any exogeneity, right? And then non-smooth is that this is for, you know, patient Hans and his value. But now if you just move some of the values a little bit, then that can induce vastly different conclusions. So this whole plot can change drastically, right? And this is not something you want to have. Obviously, you know, this has something also to do with the learning procedure that is used. I have not optimized hyperparameters or anything in that kind of rigorous way. But, you know, just going off the shelf as maybe a medical doctor might do, right? Or not him, but someone who's helping him with the predictions. So, problem setting. I'm saying that we are given an SEM or some kind of belief over an SEM and some unlabeled data. So that's the cooler part. We don't need labels or anything, right? And then we're obviously asking a question, right? I'm putting that in the given, but that's what you're really interested in. Yeah? And now the goal is going to be to construct an algorithm that can generate an explanation, which we call E, which is a reasonable answer, right? In a causal sense to Q, right? Meaning that it is faithful, it is respecting in its computation both the data set that you have, all the data samples, all the patients, but also just the SEM structure that you give it, right? So in a sense, it's also like we just discussed, right? What we're doing here, independent of whether I know the true SEM or not, which I typically don't, I just want to have a sound way of producing the explanations in the first place. As you can see, I've put an asterisk here. That's also part of the title. F will consist of linear equations in our case. You're going to see in a second why. And if, you know, our random variables are continuous, we don't have any assumptions on that. So that's cool. So we can do both discrete and continuous. But if they're continuous, we're going to assume that the exogenous terms are Gaussian distributed. Now, just before, causality is about assumptions. And why these assumptions? Really, it's put on this thing because it really gives us a way of saying that we are causal, right? It gives us justification, a strong argument for saying that we are causal. How so? When the assumptions of linearity and potentially also Gaussianity holds, then really the adjacency matrix of our SEM, yeah, which is the graph plus the coefficients, right, because it's linear equations, then they actually correspond to the causal effects. That's a well-known results from, you know, you can find it in textbooks like Elements of Causal Inference, right? And again, for discrete random variables, you just need linearity. So what this equation is telling you, really for any variable that you could look at, however you choose to intervene on any kind of value, you know, in the categories, it's always going to correspond to the particular causal effect from one variable to another, right? And essentially what this really tells you is that you can describe your SEM now as a matrix, a real valued matrix, which, or integer valued matrix if it's just discrete, where each of the entries is showing you where the arrow is pointing and whether the effect is positive or not and how strong the effect is. So you get three things and you know it's actually the causal effect, right? There's nothing else. Obviously, assuming that, you know, this SEM is, well, the SEM which is relevant to what you're considering. But that's arguably a standard assumption being done, right? And something you can iterate over. Now, we define a question. The why question we've just seen earlier. We asked something like, why is Hans' mobility bad? And I told you that really it was kind of the assertion, the observation in a sense, that all the other patients were kind of better off, right? So what you can say is that the little m of Hans was 26.2, and that's smaller than the mobility value of the average in our data sample. Where I get this average from now, I mean, I just had a little data set, right? So don't worry about that now. Yeah? If this was, not the case, right? Then, we would not be justified. Say the value was not below the average, it would not make sense to ask why the mobility was actually bad of Hans, because it's not bad. It's better than the average, right? So that's kind of where the reasoning comes from. And then, you can play the game as an analytical philosophy, right? Where we just kind of characterize this conceptual win that we got from the example. And really what we're just saying is that our question, which we define by Q for some individual I, is going to be whether, this relation, whatever you choose, is going to be satisfied or not. And in Hans's case is we are looking at mobility of Hans. So we're going to have the average value, so the mu. We are going to Hans's value. We're going to choose smaller because it's below, and that's when it's satisfied, right? So that also satisfies cases where you might ask, why is Klaus's I don't know, mobility so good, right? It would be, you change and take the greater relationship then, right? Yeah. Now let's do a first step towards an answer. Here on the right-hand side, I'm going to give you the roundabout that we need to compute these things now, right? Or to work with those. So we have our assumed SCM, and this is really not just the graph now. This is our assumed SCM, right? We know the linear equations are linear, the variables are discrete, and so -2, 1, 1, 1, these are now the coefficients which actually correspond to the causal effect. So you can say that the causal effect of health is 1 to mobility, right? So increasing health by 1 will increase mobility by 1, right? Increasing age by 1 will decrease health by 2, right? And so on and so forth. And what you see here in this little box is just patient Hans data point, right? So Hans's values for age, nutrition, health, and mobility, and the average values correspondingly in the population. Okay, so we have formulated the question. We want to know, why is Hans' mobility bad? The doctor looks, he sees all the patients, he sees Hans is kind of worse off. He knows about this now, he knows about the data point, he knows about the population. Let's go in there and get an answer. So we know now in M that health is the direct cause, the only parent of mobility. And mobility is where we start to look at. So it makes sense to look at health first. We see that the effect is, actually it's 1. Sorry, I have to type out correct this. And then, well, this again, it means that better health increases mobility. So increasing the value of health increases the value of mobility. And we observe that your mobility is below the average, right? It's lower than the other patients, right, on average. So it's bad. That's why we put the word bad. So there's really only one explanation then for observing this, right? Because again, if you increase health, mobility increases. If you decrease health, mobility decreases. Mobility is in a low value, so what's the explanation? Well, Hans's health must have been bad too, right? Because that's the SCM. That's how the data is generated, right? If this is the truth of the world, there's no other explanation. And indeed, we see that if you look now at the average of health, which is 45.1, well, Hans is also bad there, right? So we can make the same assertion we had for the Y question, saying that, well, Hans's health was already bad, right? Now, this is kind of a line of reason, line of thinking. We can continue this, right? It kind of makes sense. Okay, we have explained health now, but what about health? Health is also being caused by something. And it has these two parents. It has age and nutrition. And so we can say, reasoning backwards, essentially, along this causal chain, that age and nutrition should now be explaining why Hans's health has been bad, to ultimately then transitively explain why the mobility was bad in the first place. And well, what do we see? We know Hans is old, right? That's above average, right? And that's a key factor for his bad health, given also that it's negative, and also that it's stronger than the other ones. But then again, interestingly, his nutrition is actually above average, so it's actually better. And nutrition actually helps. Increasing nutrition helps your health, although his health is observed to be bad. So it seems to counter his bad health, but it's not enough. Again, pointing to age being the stronger factor as well. So this is what we have now, right? We have our question, we have data point, an assumed SEM, our individual, and we have now used the SEM to kind of reason with the causal effects what must be the case, right? Like what might make sense? How do we explain this situation ending up? Now we can formalize this intuition. And really what we do is we call them explanation rules. We capture them in 2 rules, really. Looks a little bit complicated. I know it's been a very dense session today, so we're not going to dive in deeply, right? But really what I want to emphasize is that there's 2 types of rules. If one of the rules is satisfied, then it's typically what we would say as the because relation. So if rule 1 is satisfied for, say, age and health, then we would say that, you know, health because of age. And if rule 2 were to be satisfied, say for the nutrition case, then we would say that health is, you know, is bad, although the nutrition is actually good, right? Although it's balanced. And you can trust me, right? When you play the game here, it's really just this assertion where you're looking at, so R1 and R2 are again just chosen as, you know, these ordering relations. You choose them, if you choose them differently, then you have either of these 2 cases holding, where alpha denotes the causal effect. So you just got to differentiate if something increasing will have an increasing effect, or whether it's negatively correlated essentially. And then you can, you know, play this game. But all of these variables, they're instantiated. It's very easy to run. And if rule 1 fires, we say this, and if rule 2 fires, we say that. Now, what we then propose is this structural causal explanation scheme. It's an explanation, as we've said, because, well, we somehow are able to explain based on, you know, the SCM, and that's why it's also structural causal, because it really uses causal and structural information. And what we can just do now is recursively apply the algorithm. And what we get in the end is a unique code. And this unique code now can be mapped to these meanings of because and although. And this will give us the eventual explanation. So specifically, let's start with mobility M and the parent health age. What we can then evaluate for Hans is that only rule 1 is going to fire, and rule 1 is going to fire in the -1 sense. -1 is a unique code. It's just saying that, you know, I increase health and mobility increases, but because mobility was observed to be bad and not good, it's the -1. Otherwise, if it was the other case that, you know, mobility was above average and health was above average, this would have been just a 1. Rule 1 would have still fired, right? It's just a specifier of how rule 1 fired. But rule 2 doesn't fire, and the modifier rule doesn't also fire. What is the modifier rule? It's just a simple thing indicating which one is the strongest cause, if there's multiple, right? We saw that age has a more important factor than nutrition, right? I could make the analog that, you know, say you go to the gym, you work out, very nice for you, it's good for your health, but obviously there's, you know, causes for your health which are stronger than others, right? For example, if you had a car accident, it's going to do more harm than what any, you know, gym session average could do, right? And yeah, then, you know, health and age, here rule 1 fires again, but here the modifier is on because it was a stronger cause. And then the other parent, nutrition, here rule 2 actually fires. And now let's just stick it together. So in this setting, we map this to mobility is bad because of bad health. In this setting, we map health bad mostly because of high age. And then in the last one, health bad, although balanced nutrition. Where do these words come from? Balanced, high, and bad. These are non-unique. These you have to fill in essentially from, well, everyday language. Essentially, it's just like an indicator of above average, below average. But instead of writing always above and below average, you know, it makes sense to use these kinds of words, right? And obviously, you would not talk about, say, high health, yeah, or low health. You would talk about bad or good health, right? So that's the only nuanced part that we have to consider. But then you can really generate this thing. So you can say Hans' mobility is bad because of his bad health, which is mostly due to his high age, although his nutrition is balanced, right? And now, as you can already see, causally speaking, this is closer to Pearl, right? So it's closer to the second work that we've seen today than the first one. But explanation-wise, it's a completely new paradigm, right? I mean, I guess, I hope you would agree that you could give this to your grandma, assuming your grandma doesn't have a PhD in, you know, computer science or something, and she could work with this better than with a heat map on an image, or say just, I don't know, a set with the values of an image. But that was really one of the reasoning aspects, motivational aspects for me when doing this work. Yes.
So what happens without this?
The average, that's a good question. I would have to think about this. I mean, I do many things, so I'm not really, so this work has been standing a little bit for a while now. We can take this offline and look there. But what I would just do is kick out that data. Yeah, so, or add a little bit noise, and then it must decide, right? So, I mean, sure, there's probably more sensible ways of designing this, but there will be an edge case, which is interesting to look at. The cool thing, which I also think here, which distinguishes it from, you know, previous works, because it's a work which actually, that's why it's in the name, structural causal explanation, structural, there's a whole graphical intuition coming from the Perl framework. You can really visualize this nicely like here. So you have either red or green nodes, really indicating, because we're just looking at the sign of the causal effect, right? And we're not even looking at how strong the causal effect is. That could be a natural extension, you know, if you want to do a master thesis or something on this. And the only thing where we distinct the values is when we have multiple potential, you know, multiple causes, and then, you know, we just choose the one which is most important. Here you could also introduce a ranking, right? Like have the top 15 or maybe sort them simply by most to least, right? But then also there's irrelevant errors. So for example, as you can see, we stopped essentially at age and nutrition. Age made sense because it was the root of the graph. But nutrition, we could have went back to age. We could have said, because age obviously caused nutrition, right? But then again, you get in kind of the cyclic situation almost, right? And so you also want to avoid redundancies and so on and so forth. And then again, because, you know, age was already part of that, we just skip that. But that's really the graphical intuition that you get out of this. And now we have, you know, various experiments in here. We also did this with Konstantin Grotkov, so we also had a little human study, right? And we tried to get some stuff. We tried to use this for learning to see whether it can increase sample efficiency and so on. But really, there's just one little thing I want to show you is that obviously you can just use now your standard structural learning algorithm causal discovery method to get an approximate, you know, linear SCM. Even in method like no-tiers, it's going to give you this weighted adjacency matrix that can be seen if you assume that this is now my SCM. You can assume this to be a linear SCM, and suddenly now you have everything you need for the SCE, right? And then you can plug it in. And now, similar to what we've seen last week with the metrics like structural intervention distance, you can get different impressions of seemingly only slightly different models. And that's a very cool thing on a conceptual level. Let me show you an example. Here, on the left, we see the ground truth actually of this little synthetic health data set, where age has a positive effect on nutrition, age has a negative effect on health, positive on nutrition, positive on mobility. And now the learned graph, this was actually with no tiers, gives you a structure which, well, looks slightly different. It just has one arrow added, which is this direct one from age to mobility, not mediated via health. And it flips the sign on nutrition. Well, if these were maybe not age, nutrition, health, but some obscure variables, right? Or if this was just a subgraph in your larger graph, right? You would say like, oh, this looks so similar, right? Maybe I'd say like, oh, I'm fine with that, right? But actually, if you look at the SCE now, it changes drastically. So the SCE you produce here is Hans' mobility, in spite of his high age, is bad mostly because of his bad health, which is bad mostly due to his balanced nutrition, right? And you're like, oh, hey, wait, this doesn't make sense. Well, what this really tells you is that the model that was learned doesn't kind of make sense, right? At least in a causal sense, believing that the scheme of generating explanations is correct, right? But this is exactly the discussion we had earlier as well in the lecture, where we said explanations itself are independent of whether what I know about causality is true or not, right? I could be an idiot in believing, you know, some, I don't know, fairy tale about the world, but my reasoning can be as precise as the one of Kurt Gödel, right? And, you know, these are independent concepts. So that's really what's happening here, yeah? And again, I would really compare this. You could maybe even see SE as a sort of pseudo metric, right? Because really it's distinguishing different causal models essentially, right? It's giving you some insights, yeah? But yeah, this is left to be seen. Let's see whether reviewers like, you know, the newest version of this work, right? If you want to check it out, of course, you can always shoot me up. With this, we're at the end. And we were talking about explanations and all these things. This is a certified classic. The ones who know this me, I've just taken the half because we are talking about neural nets, in this case, classification. And yeah, really, it's about trying to explain these models, trying to understand what's going on because we are AI researchers. And yeah, sometimes it can be something as naive as just trying to understand, like my model is saying it's a dog, although it's a cat, right? Maybe it is a dog, and I just think it's a cat. And with this, here are the key references from today. And yeah, I think we are over time. Thanks for staying with me. And see you next week then, according to plan.